that throughout the last couple of years, I gave many times, at least 20 times maybe, but it's been a while since I gave it the last time, and I just realized I don't really have a nice fitting presentation that I could just reuse. So I made a new one, a very short one. And also I realized that so many things have changed since I first gave this lecture. And the reason why I even put it together was that I was teaching at a university in Zlín in Czech Republic, and there is a study program for designers, and also some I think also some cultural studies, art studies in general. And they were not aware of the computational design at all at that point, but they had. But as I experienced before, everybody has some preconceptions. Everybody feels like, well, mainly when it comes to the architecture and when it comes to computers being involved in art and architecture. So I put together a presentation where I was explaining how the computation could affect the creative disciplines, mainly in architecture. And just for myself, I built up a hierarchical system of how computers can be involved in the creation of architecture. And as I told you, things have changed meanwhile, and not everything fits into my system anymore. But still, I would like to present to you the hierarchy that I made up. Explain it to you, and maybe that would be super nice also for me. We could discuss later on your opinions, ideas, and experience on that, because there are some things that don't fit the system. So this is called From Automation to Design by Behavior, and that's because I identified 3 different levels of computer involvement into the creative discipline of architecture, starting from design automation, through parametric design to emergent design. And you see that there is a level 4 called design by behavior, and that's something that I'm proposing, and I will just come to it. I will build up to that. And there are some orthogonal approaches, something that doesn't really fit, and that's explicit versus implicit design. That's another thing that together with Tomáš Told, we wrote an article about. I will explain that to you. That's something that we would really love to explore further on. As I told in the previous debate, we are always trying to have some agenda, some main project that goes throughout years and jobs and applications. And this was supposed to be the one. This making a distinction between explicit and implicit design. I will explain that. But then there are discrete aggregates that we instead started doing recently, and I need to figure out where do they fit actually into this scheme and hierarchy. So let's start with level 1. I think I cannot really avoid repetition. I said some of these things in the previous part, but I will repeat myself here again. Very often when I was talking to architects or lecturing or having some sort of debate with architects about computers being involved in the creative discipline, there are many things that they say. Some are resilient. Some say that just relying on computers or architecture is dangerous, and also it takes the jobs, and it's inhuman, and it takes away all the creativity. I completely disagree with all of these things, but that's something that I hear all the time whenever I'm giving a lecture with architects. They eventually ask me, and don't you think that it's like you're losing the human touch when you're so much using the computers? And that's certainly not it. So those are the people who don't like it at all. But then there are people who are not really doing that stuff, but somehow they are interested, and somehow they want to approve of that. And many times they say, okay, that's cool. We don't have to worry about the computers because they are just advanced drafting tools, advanced pencil or advanced ruler and pen. And I don't think so either. I think there is something fundamentally different with the computational design and approach that changes the discipline, any creative discipline, to be honest, in a way that you as an author do different things, think in a different way, and the results are different. And I will just explain to you how do I identify that we can involve the computers within this process, and when is the moment when the computer eventually makes a difference. So the first level is design automation, and there is no difference, I think, or I identify, between the conventional design when you have an idea and you use a pencil to draw the idea and just to mold the shape of the architecture based on your idea. Design automation is what computers are good for. They are good for drawing a lot of similar things and making some things automatically and faster and easier. And they can, well, that's what they were made for. Somebody is commenting. I will just, yeah. Kism says, yes, I think human brain is intelligent, but in some point it will be overburdened. So we certainly need in future a computer brain. Yeah, exactly. But we also need to somehow moderate or somehow be involved in the creation. And I'm going to propose how can we use the computers in a smart way. So anyway, so the design automation is that something that what AutoCAD is doing for you, or basic CAD programs. They do that for you. It's easier to draw something in computer than in hand for me, at least. It's easier to produce a lot of drawings in computer, and yes, in a certain way, that's a little bit more advanced pencil for you. Somebody is asking if I can do something about the audio. What is wrong with audio? Can somebody from YouTube explain what is wrong? I can do, but I would like to know what should I do. Anything wrong? I will stop sharing a little, and then I can change settings here. Where was that? Audio settings. Yeah, it seems like my audio works well. It's a bit dirty. Okay. I will switch to a different phone now. And you can tell me if it's better for you or not. So I will use this microphone now. Okay. Somebody else is commenting that the audio is fine. I will keep using the original audio because that's proven probably well. Anyway, let's go back. Let's go back to the presentation. Also, I need to focus a little bit. Anyway, so let me explain what you can see at the picture here. When I was first giving this lecture, I was like, how can I use the computer to actually do things for me really fast? And I just decided to spend exactly 30 minutes to make a grasshopper definition that actually generates a skyscraper only based on very few input parameters. So one of them was the core axis, and then the number of floors and thickness and so on. So in 30 minutes, I managed to reach this stage. So I had a grasshopper script that actually could generate something like this. And I could just pull sliders or change the core axis shape, and it actually generated new and new versions for me. But at this point, this is very useful. But when you think about the design process, it's exactly the same as if I was drawing by hand. It would just not take me 30 minutes, but probably a couple of weeks to actually draw each of the versions, which is not bad, but it really doesn't change the discipline fundamentally. I can show you something that is coming from our own office, and something that I can refer to as something that we did really in practice, and it's this project. I will talk about it a little bit more with Tomasz on the Subdigital day. At Subdigital, we actually also create architecture models, but they are not the usual like cardboard models, but this one is made of steel, glass, and acrylic, and there is also a custom LED pixel display inside, and there is a computer and all these electronics. But what we did was that we designed the whole thing parametrically, so that it's made of almost 3,500 pieces. Each one of the pieces is different, and they all should fit together perfectly on a click. And if you imagine how much work that is, it's not really possible to do it manually. So we had a lot of small Grasshopper scripts that were actually doing this for us. They were making sure that whatever change we do for the shape, everything works well. So they were actually creating the shapes of the pieces automatically and making sure they work. They were also doing a lot of checking and testing. This is also how we use Grasshopper. I also made a tutorial for that. I call that GHLint. That's actually that's an approach where you are working with Rhino or the main software, just like usual. You're drafting just like in AutoCAD, but there is a Grasshopper running in the background, constantly checking if everything is okay. And if you do something that doesn't work well, or doesn't, in this case, something doesn't fit, one part doesn't fit another part, it tells you. It actually throws you a warning that you should check certain parts, that this doesn't work. So that's here. I would like to demonstrate that this helps a lot. The computer helps a lot, but doesn't change the way we work fundamentally. We wouldn't be able to produce something this complex without the use of computers. Actually, what you see here on the right side, that's just one of the floors here, and we've got 46 such floors, plus many other things. These are the floors, and they consist of so many parts here. So we use the computer to actually automate a lot of processes for us, but still we somehow worked manually in a way. And the result, we didn't design the building itself. We only designed the construction of the model that is 2 meters high. So it's basically as tall as a tall person, and it weighs 350 kilos, so a lot for people, maybe more. Anyway, and the result is works well, performs well, and everything fits. All the parts fit together, mainly because we used computer automation and computer testing for that. But it didn't really change the way we would work otherwise, also manually without the computers. That's design automation. That's basically what mostly happens when the architects are using computers as drafting tools and as blueprint producing tools. The next level is parametric design. That's this is a bit of a tricky term, because when Patrick Schumacher is talking about parametricism, he's talking about something different. But parametric design, well, it's a discipline. Parametric modeling it's a discipline, it's a technical discipline. But here within the architectural and product design realm, I think we can identify certain things that could be called a parametric design. For me, it is that when the whole thing consists of smaller parts, and each one of the parts is somehow reacting to the environment. In other words, if you look at this shape, there are little bumps, and these bumps are, you can understand them as panels or as little pieces that make the whole eventually. But each of these bumps is checking its environment and doing something. For example, this one is checking the curvature of the shape, and also the Z position, so the vertical position, and maybe it's also checking some sunlight or whatever there is, and then it changes its shape or its properties. and each one does it. So each one of the panels makes some sort of decision, and then it modifies itself. So you end up having a lot of pieces. Each one is from the same family, but they are different in the implementation. That's something that I was talking about as well, that the computers actually do the implementation for us. And I, as a designer, I decided the rules that were driving these elements, and then they were automatically applied. But you can see this as a one-time process. It happens once. Each one of these elements is looking at itself and at the environment. They don't really care that much about the neighbor, because that would become way too dynamic, because the neighbor can change as well. So not only the element is changing, but even if it was reacting to the neighbor, and the neighbor could be changing as well, then they would constantly negotiate with each other and change all the time. So now each of the elements is looking at itself and making some sort of decision and getting some other shape. Here, we are eventually coming to some difference between the conventional design and computational design, because this is something that you can do manually, but it becomes very difficult, and you wouldn't probably do it manually. Even if the elements, if there were not so many elements, usually in the conventional design, you don't think this way, that you populate the object that you are designing with elements from the same family and strictly based on data change their properties. You do that with the parametric design, and we are slightly shifting from the conventional to the computational, and this already makes some sort of a difference. Again, from our office practice, we did something similar for this exhibition. You can see this is an exhibition called Human by Design that we made last year and this year. We actually uninstalled the exhibition a month ago in Vienna. It was at the Museum für die angewandte Kunst. And the exhibition was made for the Slovak Design Center, and it was installed there. You can see that there are these like tables. We had 54 of those. Each one is different. Each one fits to the rest, like to the system, and each one has a different plinth, different table legs. You can see it here. Hopefully, it looks good on the broadcast. We populated the gallery with some cells. Of course, this is just a very simple Voronoi diagram. I will talk about the use of these straightforward design tools like Voronoi later on, but here I would like to demonstrate something else. So we generated a system of similar cells. That's what I was talking about before. Each one of these cells has a potential to do the same thing. Some of them changed to a table, some of them didn't. So that's one thing, one decision they made based on certain parameters. And the parameter was what you can see here as these isocurves. Basically, we created an undulated surface, like a landscape. And if the landscape was tall enough, then a table grew underneath the landscape and copied the height and inclination of the landscape. So that's another decision that each of the cells made. And also the shape is always based on the position, so that they fit well. And then we generated a lot of legs for these cells. This is something that I think is truly parametric, because each one of these cells has a potential to become a table. Only some of them did. Each one of them has a potential to be tall or short, but each one of them adjusted its height to certain parameters that came from the outer world. And then each one of them had its legs generated so that it actually is stiff and stable, and we don't use too much material. So we also did some optimization. So if you think about this, you could do this manually as well. It would take a long time, but even if you are doing that manually, you would have to be thinking somehow digitally, or you would have to take data into consideration because this is all data driven. And I just realized that I would really like to show you one more diagram, and maybe I didn't plan to originally, so I need to look it up on my computer. But that will show you what do we actually tell to our clients, how it is, why is it important to, here. What does it mean to use parametric design for in the real world and in the production, and why is it efficient also for the client? But again, this is I'm checking the chat. What we have done there is it related with the exhibition theme? Yes, it is. Coming back to the exhibition, let me show you here. I need to this. We'll talk about that one, about that project in a different day, in the Subdigital day. But yes, it was related to the exhibition. The exhibition was about sustainability and innovations in design, in order to we were showing well, the authors, the designers were showing 13 different projects. Each one of them was dealing with sustainability and some sort of innovation that brought ecological aspect to the product design. So what you can see here is this is a fashion made of fully recycled materials and new experimental materials that were based on fungus, I think. Here there is an exhibition of different materials that the design center is actually putting together a library of materials where you can actually try the material as a designer. You come to the design center and actually hold a piece of the material in your hands and read everything about the material, including its carbon footprint and all these things. So we had 13 different exhibitions like this. And also, what we did here is related to that because, yeah, this is actually what I wanted to show you with the workflow, but I will tell you here. The design process, well, as a job, this exhibition, it was really nice because we liked the content and the collaboration. But if you think about how many people were involved, and also they were mostly they were artists and they wanted to finish everything the last moment. The problem was that until the last moment we didn't have the exhibits. We didn't have the pieces that we were supposed to put on those plinths and platforms. And we had to be ready to produce that all these 54 tables last moment. And if you think about the design, the production process, which was first you had to do the blueprints, then you had to laser cut the metal, then you have to CNC mill the wood, then you have to print everything, and then you have to weld it and put everything together. There was a lot of work that we had to do, and we knew that everything will have to be last moment. And therefore, the parametric design helped us to actually produce everything last moment. We were able to wait for the artists to give us the exhibits, the pieces, and this is something that we are showing in this diagram, which I originally didn't want to show you, but this is something that we are now showing to our clients. With the conventional design, which you have here, you got the assignment and then make a concept, and then you just manually produce design, ask the client whether he or she likes it, and probably not. So you've got version 1, and then you need to sit again, start from scratch and redesign it again, and you've got another version and so on. And it takes time. And eventually there is a production that is usually done by people. So the blueprints and the documentation and notation, you actually make for people. So it's done by people for people. You make blueprints that you make yourself, and somebody who is a human is actually reading them. With the parametric design, we are claiming that it's slightly different. Reality is a combination of these two, but this is our claim, that you get an assignment and make a concept that you have to do all the time. Then you collect certain data. In our case, the data was the landscape, and also we were collecting the data about the pieces that we are about to exhibit. Then you make a parametric software, you design the parametric software. In other words, you make the grasshopper definition, which takes time and is expensive. That's why it's the huge red square here, because it's not easy. It takes time. And if you understand this as a timeline, at this point in the conventional design, the client would already see the first version. With the parametric design, the client doesn't see any version here. And probably the conventional designer would be halfway in the second version. Then we have the computation part, which sometimes actually is quite slow. Even with the grasshopper definitions, we make them sometimes so complicated that maybe it takes a day to produce something. Even with the tables that you saw, it took a couple of hours to generate the legs. So it also takes some time, but eventually you can have a lot of versions at once. And then eventually here, the client can see 3 versions. Here, I was claiming that the client can see 8 versions, but you understand that maybe it can be 100 versions, only based on different data. So you feed the software that you made different data, and then you produce different results. And with the results, you either pick one that fits you the best. And it's easy to pick one because this is all based on data. It's not a drawing, it's data, and you can evaluate it. You can create another grasshopper script that is a fitness evaluation function that will eventually check whether the result is fit or not. So you can select the one that is most fit, or you can select several and combine them, and then you produce it. But here we are saying this is not a production, it's a fabrication, because very often you are producing data not for a human being to produce it, but for a machine. So in our case, we were producing data for a CNC mill, for a laser cutter, and we never had to actually make blueprints with dimensions and annotations. We never had to, which actually takes a lot of time to draw everything so that the worker on the building side can actually take a taper measure and see if the size fits. We didn't have to do it here because we were actually generating data directly for the machines. That's not entirely true because this is welded by manually, but we actually generated a lot of drawings automatically that we gave to the welder, and we went there to the workshop with the welder, and we were just putting everything together with the welder. But again, it was really fast and rapid. But still, you see that this helps a lot. This brings some new quality to the production, but eventually the design is not, even the result is not fundamentally different, and even the process is not from a different universe. It's still somehow like an evolutionary step towards something that is more efficient and slightly nicer and works better, but it's still not a fundamentally different approach. Here I would like to show you the first moment when the computation is fundamentally different, something that is a completely different universe of solutions and approaches. And that's the emergent design. And this is something that is already happening quite a lot. When I first was talking about it, it was not so so prevalent. Emergent design, emergence. I'm again reading a question. So no, I will answer the question now because it's probably related to what I was saying. So how about the shadows? Are they also included with the parameter to the approach? You can. Here in this case, it was not. So we didn't really care that much about shadows in this case. But with the parametric approach, all the data that comes into the algorithm, you are the one who is selecting the data. You are the one who's making the algorithm. So if shadows matter to you, then you can incorporate some shadow evaluation or shadow-driven decision making into the algorithm. Of course, it doesn't really matter what the inputs are. And I will also talk about motivations. I think it will be in the hands-on part today. what can be the motivations, what can be the decision making then that you make when you do the computational approach. So in our case, we didn't care about the shadows, but I can imagine that that can be incorporated as well. Anyway, let's go to the emergent design. Emergence is a phenomenon when a complex final thing consists of smaller elements, and the elements have certain properties and values, but the complex thing is more than a sum of these properties. So if two things, well, actually, let's talk about 3 or 4 things that you can read what they are and what are the values that they represent, what they mean. They create a new synergical effect that is not part of that you can read from the individuals, but together they do something that is more than the sum of what they are. This is in thermodynamics or in chemistry. It happens a lot. You get two elements, and each one of them they don't do anything, but when you put them together, there is a reaction, and something completely new happens. That was not, or the result or the process is not really embedded. You cannot really read it from that. This is for more reference here. It's amazing to watch some lectures by Manuel de Landa, who is a philosopher, and he talks about all these things in a very, very nice way. But I also think that this is something that Deleuze was talking about when he was talking about the diagrams and rhizomas. This is, for me, this is very hard to access. I don't understand it properly, but I think that the interpretation of that is that that you can understand the whole thing as a complex system. Okay, let's stop here. I will talk about complex systems a little, and then it all comes together. The complex systems are mathematical models. When you have an environment, you can imagine an aquarium. That's the environment that it's got some boundaries. There's some water. There are some stones on the bottom, and that's the environment. It's an easily observable environment where something is inside, and inside you've got some fish, and you've got some fish that eats plants, some fish that eats other fish, and the fish, they do something. They interact with the environment, so they either go with the flow of the water, or they hit the glass of the aquarium, or avoid the glass of the aquarium, or they eat the plants that just are in the environment. And then there is other fish that are hunting these fish, and maybe the first ones are escaping from them. Maybe the other ones are just hunting in advanced ways, and so on. So, but every single element has its own mind, behavior. It does something, and if you observe the whole system, it seems like there are some patterns. Something is happening there that seems like a plan, like an overall plan, but in fact it's not. It's completely bottom up, based on the small elements that interact with each other. And the plan that you observe is the emergent phenomenon, something that you cannot observe in the individual elements, but altogether it looks like a systematic, meaningful thing, which it actually is, because it's completely deterministic. It's based on certain behaviors. You can trace the behaviors. You can understand why this is happening, but you cannot really predict it just by looking at the elements, or just by looking at the system as a static thing. If you just make a photograph of an aquarium, you cannot know whether the fish is actually swimming fast or slow. You need to see the difference between two moments in time. So this is a dynamic system, and that's a very interesting notion, and you can actually use it for generating architectural systems. Mostly what we are doing is a simulation of some natural behaviors and phenomena. That's what when Eva was asking me whether I get an inspiration from nature, I was hesitating a little, because in a way I do, because what you're looking at right now in the presentation, that's a simulation of a flocking behavior. Flocking is what fish are doing, what birds are doing. When you see a flock of birds and it looks like a cloud that is changing shapes, it's because there is certain behavior with birds that actually, sorry, that's Zoom converting the previous part of the presentation. Anyway, so the birds, they have certain behavior. They are flying with a certain behavior, but they are not planning to make the cloud that looks like the way it looks. The overall look of the flock and the motion is the emergent effect of that. And we can very easily simulate that. We can simulate even ant behavior. When there are cows or sheep, they also move in a certain way, and so on. So what you're looking at is a simulation of a bird flock that actually is not only that, but there is some more behavior, that the environment is something that is attracting the birds. So imagine a flock of birds trying to eat something from trees. So they're attacking the tree all the time. But the real thing that I was doing here at this picture, actually I should tell you what it is. It's a corporate identity for a company that is auditing internet safety. So it's a company that prevents other companies from getting hacked by hackers. So they use this as their background picture, and it's part of their logo and so on. And there is one type of hacker attack on a website or some online service that is called DDoS, which means that a lot of computers worldwide infected by a virus are accessing one website or a server, which means that the website is not accessible for others because it's completely occupied by those infected computers. So imagine that you would like to check your email, but your email server is not responding because it's completely stuck with these random infected computers trying to access it all the time. So it's basically just making it way too busy to be accessible when it's needed. But if you imagine that, what is actually happening is that there are some birds flying around that server and trying to attack it all the time, or maybe you can imagine it as wasps or whatever. So they are flying around. Whenever they can attack, they do attack. And on this picture, the server is basically some sort of a network of wires that are glowing. You can see the glowing wires here, and there are these attackers flying around trying to hit it all the time, and they are leaving a trace behind, just like when the planes are showing off, they leave a smoke trail. So what you can see is a smoke trail of those attackers, and this is the shape that happened. But the shape is completely emergent. It's not embedded in the elements. It's not planned. It's not planned to look like this. But the behavior is completely well known. The behavior of the elements that are creating the result is perfectly known upfront. And this is a completely new notion. At the beginning, when I was designing this, I didn't know how is it going to look. I didn't have a faint idea that it would look like this. I knew that the visual will come from certain family of possible visuals. I knew that it's going to be blue. I knew that it's going to look like a mess, but I didn't know exactly that there will be a twiddle here, that there will be a tail here and a mass here. I didn't know that. That happened, but I know exactly what is the behavior that created that. So as an author here, what I was designing was the behavior actually, and not the shape. In other words, I didn't implement the shape. I implemented the idea. I had the idea at the beginning, the intention to actually make this sort of a simulation. I implemented the simulation itself. I chose the behaviors. I chose the environment, the data, and the formal implementation happened. And this is something that you can do with architecture as well. you can see architecture as a complex system of individual elements, agents, participants that actually generate the final shape and result. This is very easy to imagine within a city or an urban structure, where you see that it's made of small parts and buildings, quarters, and districts, blocks, and these are somehow negotiating with each other. But this is not really the full potential of this. It can go much further, and you can actually make a simulation that generates not only urban structure, but even you can think of a smaller scale. You can think of a block that consists of certain elements that somehow negotiate between each other and do some sort of fighting until they stabilize somehow. Or you can think of a single house that is made of elements that are somehow fighting with each other at the beginning, and then they find some equilibrium, and that's your shape, and you don't know what the shape is going to be. Or you can go to a smaller and smaller scale. And the thing is that we really wanted to implement something like this into practice. We wanted to produce something that actually shows that this is possible to implement, to bring this into reality. The problem is that it's difficult to find a client that will give you $1 million or $2 million just to experiment, and without telling the client what the result is going to look like, because that's the fundamental thing here. We don't know what the thing will look like eventually, so nobody will give you a budget for that. So you need to go a little bit smaller than a house. So you can make a pavilion, but still that will be very expensive and we didn't have the budget. And you can go smaller, you can make it furniture, which is already doable, but still it's kind of a too big approach. So we decided to take the simulation to the smallest possible scale, and we made a series of jewelry. Actually, I've got it here. I can show you on the camera. So we 3D printed a jewelry set that was completely designed with the simulations, with the flocking simulation. And this is something where we can actually demonstrate that this can generate forms. The forms can be materialized. They can be 3D printed, for example, in this case, they were 3D printed. And then they can become real. So this is not just some exercise, or this is not an exercise in form making, but this can actually become a real thing. It looks on the picture, it looks like it's big, but I can show you it's really tiny. We 3D printed the whole thing from a stainless steel metal, and now the jewelry is here. I didn't really plan to show you, but I do. The ring that you can see over there, it's this one. It's really tiny. Anyway, it doesn't focus well, so yeah, maybe I will do that. We will talk about. I'm going to talk about this later on today. There's a question. Is this idea that not knowing the last form make you scared? Whether I'm scared of not knowing the final form? Actually, not at all. And this is not scary, because the thing is that I'm well aware of the principles that generate the form. I'm well aware what are the forces and behaviors and decisions that actually generate something that you can see here. All these parts, like this is also a recording of some motion, so that's why it's a linear thing. It was growing from the left to the right, and I knew in every time step what is the decision that all the agents that are generating the form, what are they thinking, and I know what they represent, because they are called agents because they represent some. They have the agency. They represent some notion, some intention, some behavior, and I knew exactly what it is. And I think this is actually a very good approach, because if you know what the intentions are, then and you know how you implement it. If you implement it well, then it's completely reliable that the intentions are somehow within that. So the only thing is what the intentions could be. And the final result is so rich in form and in connotations and in relations that I wouldn't be able to do this using any different method. That's the thing. I can make something that performs better, is more complex, takes into consideration more aspects than with any other method that is available. The thing is, why does it make sense to simulate a flock of birds when you are designing an architecture or even jewelry? And that's the problem. And at this point, we are coming to something that I call design by behavior. And I tried to write a couple of articles on this and essays to elaborate what design by behavior might be. Because when I was explaining that I know exactly what is happening in any time when this was generated, the thing is that I know that this is a simulation of ant behavior. I know what ants do when they are moving. I know what decision making they make, but that's completely unrelated to architecture. And here, I just took an existing behavior and used it to generate a form. And I think there is a responsibility of an architect, of an author, to actually come up with the behavior itself that is meaningful and eventually creates some emergent, unknown result. And that's the design by behavior. You design the behavior, literally, you design behavior of agents, then you start a simulation of a complex system, and then the result should be a result of those behaviors. And the question is what the behaviors are and should be. And this is something that has proven to be a very hard question. I don't know, and I don't know how to design the behaviors to be truly architectural. Because if you think about a city as a complex system, then every stakeholder in the city, every property developer, every house owner, every municipality, they have certain intention. They want to achieve something. Somebody wants to make money. Somebody wants to make a nice park for children. Somebody wants to make a road so that more cars could pass through. They have their own intention. And you can somehow make a simulation. You can turn that into some virtual agents, and they can fight with each other and find some sort of equilibrium where everybody is so happy. And you can do that in the computer. But the problem is that as a result, you will get an emergent system that will embody all these already known intentions. So the road will be wide enough, the park will be there, the building will earn enough money, enough people will be housed. But that's something that you can already read in the small elements, in the agents. And therefore, the result is not truly emergent. It doesn't really bring a quality from a different world. It's somehow embedded in the agent. So design by behavior is a huge challenge that I still haven't figured out properly. But the challenge is how to design architectural intentions so that when you make an algorithm that is actually making a simulation that is taking all these behaviors into consideration, you get a truly emergent result. And here, I think that what helps me the most is what Peter Eisenman is talking about when he's talking about his work. He has a completely different set of notions that he wants to embed. He's talking about the anteriority, like the historical evolution of a place. He's talking about some semiology. That's another thing or capacities that elements, they have certain, this is not Eisenman anymore, but they have certain affordances, something that they could become or could do possibly, if like they have a capacity to become something or to perform in a certain way. And these are abstract concepts enough that are systematic, but eventually could create a system that brings new qualities, and the qualities could be, and even behaviors could be architectural, and the qualities could be from a different level of architectural perspective, like usability, or you can read cultural interpretations and so on. I think something that is coming this direction is the artificial intelligence that Daniel Bolojan is right now teaching here at the Digital Futures. He is just making some sort of fictional landscapes that are somehow made of a neural network that is learning something. But still, the intention is that you can make a system of negotiating architectural agents that do certain behaviors and eventually create something bigger. The thing is that this concept is so complicated that I don't have any picture. I don't have anything that I could show you, but there's a couple of articles that we wrote about this, and we are just encouraging other people to think about this concept. Because I really believe that if we can achieve this complexity with just simulating nature and ends, imagine what sort of complexity could we achieve doing something that is more meaningful within architecture, being more architectural. I will just very quickly go through the last two notions, and then we'll make another break, because as far as I know, we are supposed to finish quite soon. So yeah, we were supposed to finish at half an hour ago, and right now we were supposed to start with the next part, but I will make the next part shorter so that we are back on the schedule, and so that you don't really miss anything from the rest of the digital futures. But let me talk about this a little bit. These are two different approaches that don't fit the hierarchy, the four steps: the automation, parametric design, emergent design, and design by behavior. This is something different. First one is explicit versus implicit design. That's a new notion that we brought up last year in an article. And the thing is that in the conventional design, the designer takes, imagine a facade. In the conventional design, the architect sees the elements as parts of the whole. So you've got a facade and you're putting windows on the facade and doors and whatever ornaments, or you come from within, or just looking at the facade or doing something like that. And the idea is that in conventional design, explicit design, you just take a window and move it a little bit to the left because it looks better in the overall composition, or a little bit to the right, or just you make a little joke that one of the windows is slightly tilted, and it's funny because with the rest of the facade, it's something that stands out, and so on. But the idea is that you explicitly define everything in absolute terms. The reference that you have is each element is referring to the whole. So basically, it tells you all the information. And this distinction, explicit and implicit, comes from the computer science. When you're programming, there are two different approaches. One is explicit, one is implicit. The explicit is that when you want the computer to do something, you provide all the information. Versus implicit, you say, you rely on something that is called a state machine. So you know that the computer is in a certain state, and you say, whatever the state is, change it. I will give you an example. You can have a power switch for a lamp, and you can have a power switch that only toggles. So it means if the lamp is off, you push the button and then it's on, and then you push the same button and then it's off. So it's referring to its current state. The lamp is in whatever state, and you change it to the opposite. And then you can have two buttons. One is always switching the lamp on, and one is always switching the lamp off. That's very explicit. we're explicitly saying, I don't care whether it's on or off, I want it to be off. So we switch the, you push the off button. And when you only have one button, it always matters whether it's on or off. And the button does something else. And you can do the same with architecture, and it's a super simple idea. You either put the elements in absolute terms, in absolute coordinates. You can imagine that you have a landscape and you are putting the houses on the landscape, and you are always defining also where the house should be, and so on. Or you just say, okay, I want the house to be next to its neighbor, I don't know, 5 meters away. In that case, you are implicitly, you know that there already is something that you can refer to that is next to what you are doing. So you're there. You need to take into consideration the rest of the elements, and you're referring only to local conditions. This is something that we haven't developed much further. But I think that's very close to what the animation architects were doing in the 90s, mainly Greg Lynn, where he was also talking about why everything should be a smooth curve, because each position of the curve is referring to the position before. So the spline curve is actually smooth because it's a fluid flow. But you can also think about this as a grid, where every single node of the grid, when it moves, it also drags the rest of the grid, and so on. So this is something that we wanted to explore and maybe teach to the students as well, because it's a simple concept that can completely change the result. And again, this is completely orthogonal to what I was talking about before, because it's not related, and you can incorporate it there or not. Like it's completely independent. I just realized that maybe I could develop this a little bit further and make some diagrams to make it a little bit more understandable. I hope it was not too confusing. The very last notion of this part is the discrete aggregates. That's the object-oriented ontology and discrete element architecture, just like people at Bartlett are doing, Gilles Retzin or Manuel, who is going to be our guest one of these days, Manuel Jimenez Garcia. And we will talk about that later on. The thing is that you can generate the whole architectural form out of discrete individual elements that somehow connect to each other, aggregate, but create a bigger thing just by connecting smaller elements. And you either have one single element like a voxel or something like a ball or anything, or you have different elements available and you just connect them in a way that it creates the whole thing. The thing is that this doesn't also really fit the notion of these levels of computational involvement, because it's completely orthogonal to it. The idea is from a different understanding. So you can actually do both of these things on any of these levels. And for us, also at Subdigital and also at a research platform that we are still maintaining, what we are going to do right now is that we are going to connect the discrete aggregation somehow with the emergent or even emergent design or even design by behavior, because there has to be a way how to connect these things and how to actually work on the pinnacle of what the computation can do right now. Because the ambition, the aspiration of our work is always to push the possibilities and push the discourse a little bit further. That's what I was talking about when I was talking about the critical architecture. We don't really care, like we do care about the craftsmanship and perfection and skill building, but that's not enough when we evaluate our work. We need to push the work a little bit further and bring some sort of novelty that is also conceptually new and still relevant, still being contemporary and reacting to what other people are doing. And I think this is something that needs to be combined at the moment, the discrete paradigm together with the emergent paradigm, which still is very underdeveloped and needs to be tested further on.